the oceans are young. The oldest rocks in the oceans are less than 200 million years old, and they're sort of made of the same stuff. It's this black basalt that we see in all these here.
We find large amounts of carbonate in the oceanic crust, and that's basically a way of naturally sequestering carbon, which comes from the atmosphere, is taken up by the ocean, circulates through the crust, but precipitates as minerals there. So we're trying to understand that process better and how much of that contributes to the global cycle.
So understanding how the oceans exchange chemicals with the ocean crust is a key component of the carbon cycle. It seems that at different times in Earth history, for example, we go back to the Cretaceous when CO2 was much higher. For example, there was much more interaction with the ocean crust, and if you look at those sites, they're packed full of carbonate. If we go to younger sites, there's some but not much carbonate. So, we now are able to understand how the ocean crust and the oceans exchange elements and how they buffer the chemistry of each other, really. That's kind of important for our understanding of the Earth system, and that affects climate at a planetary scale.
So by looking at these sediments and these records of past climate events, we can really learn a lot and hopefully predict better how the climate might evolve in the future, especially given our increasing anthropogenic sequences. By drilling the sediments on top of the ocean crust over this age range from 60 million year old crust to 60 million year old crust, we hope to get a really high resolution record of very important climatic events where we went through a hot house and a cool house, so basically times where the CO2 concentration was as high as it is today, or even higher, maybe twice as high, what we might expect in the next decade, or potentially even into the next century.
If we don't do something about it.
Correct, yes.